So I'm happy to introduce Olindo Isabella from Technical University Delft, who was born in Naples and studied also there in electronic or electrical engineering, and then moved to the Netherlands to do a PhD in Delft, where he graduated in 2013, cum laude at the university there on a PV thesis. And then he was invited to stay on the faculty there, leading his own research group, later also the PV Materials and Devices group. And now there's an even bigger PV technology center that goes all the way from materials research to devices to systems in Delft, really showing the university is investing a lot in this technology under the leadership of Olindo. The lab is also very well known for their organizing international conferences, workshops, and in particular online courses. I was just checking when we were talking here online. Just Google Olindo Isabella and then you go find online learning in Delft. And you find courses that you can just click on and follow and learn about PV cells and modules, systems and electronic components, networks, grids, all the technology that's around PV. And it's all online, open, available. It's a fantastic initiative. Hundreds of thousands or maybe even millions of people have looked at these courses over the years from all over the world. So that's another way to create a very large impact. I also want to mention, before you start, your scientific work, in particular the tandem solar cell on the silicon perovskites that came out with more than 30% efficiency for 4-terminal. A few years ago already, that was a key element for us to put in the solar NL proposal as an example, how fundamental and technical science in the Dutch universities lays a basis for all the company programs that we're financing now. That was also due to your initiative and colleagues' work. So now the floor is yours.
So thank you very much, Albert. I'm honored to be on this stage. And of course, especially the last result could not have been achieved without the national coordination with also other research groups. Today, of course, the talk is more about single junction devices, crystalline silicon solar cells. And I take the opportunity to thank my co-authors, Paul Procel and Yifeng Zhao, but also acknowledge the immense work done by the rest of the team working on crystalline silicon back in Delft, with a couple of alumni already spreading somewhere else, Sanan at Sun Yat-sen University and Guantao Yang at Trina Solar in China. So let's start first for people that do not know the PV in the group. We are indeed working on the whole value chain from atomistic scale up to kilometer scale at low technology readiness level, of course, as a university. We work on solar materials, hybrid tandem devices, PV-based multifunctional modules and the XIPV systems. And these 4 experimental areas are supported by 2 cross-cut thematic areas that are circular photovoltaics and as well as photovoltaic multiscale modeling. So this is our group. We welcome you to visit us when you want. And with this, I would like to focus indeed my presentation on crystalline silicon devices. There are several motivations why to do that. First, we have several certified efficiencies that have been announced one after the other very quickly last couple of months, especially from big industries, top-tier manufacturers in China. And this is because the state-of-the-art structures are essentially touching very much the Auger limit, also enabled by excellent manufacturing and excellent crystalline silicon wafers. Examples are the front-back contacted solar cells based on either polysilicon or silicon heterojunction technologies, as well as interdigitated front-back contacted structures that also have reached 27.3% on a large area lately from Longi. And this is also reflected in very high efficiency PV modules. Maxion presented almost 25% designated area PV modules that are really impressive when it comes to also shade resilience. That indirectly means that their solar cells are also in the range of at least 26.5%. Another motivation is that PERC, that is the current king of PV cells production, is quickly subsided by TOPCon technology. And later on, there will be room for silicon heterojunction and also, of course, IBC cells. And this is mostly because of lower capex and the better compatibility of TOPCon with respect to silicon heterojunction. Another important, of course, motivation is that in the long run, we will also need to go over the single junction practical limit. And this is, of course, exemplified by fantastic lab-scale results that have been achieved between KAUST and LONGi, but also from a myriad of many other groups around the world. And also, very recently, the 25% module that has been certified between Oxford PV and Fraunhofer, that is a full-sized module made up of tandem devices on M6 wafers. So this is also very important to say that although we are coming, and I agree with the previous speaker that we are coming very quickly towards the ceiling of the crystalline silicon technology, there is still a lot of interest in studying and understanding different type of architectures that can be also interesting for industrial exploitation. For example, lowering the capex or being functional to future tandem device architectures. So the objectives of my slides are threefold. First, we look into the working principle and transport mechanisms in crystalline silicon solar cells, focusing on a low thermal budget technology, silicon heterojunction specifically. Then I will illustrate what we have been doing in Delft, from front-side passivation up to back-end metallization, on how to improve our game, to step up our efficiency in the last couple of years, and then plugging into that knowledge into our modeling framework. I will also present our numerical optimization in both FBC and IBC architectures towards efficiencies well above 27%. So first, chapter. Before working out this information, I would like to introduce our modeling method, because nowadays solar cells, those that are really close to 27%, have extremely low saturation current density. They have minimized the contact resistivity, and they also have an incredibly high lifetime of minority charge carriers. Meaning that we need to really go into hard, deep details of how the physics inside these architectures work in order to find the subtle differences between a top cone or a heterojunction that are running at almost 27%. So we need to numerically simulate the semiconductor equations in a full-blown detail with the finite element method. And to do that, we need a number of input parameters. So this is a little bit cumbersome part of our work to gather all the database of information, optical data, electrical data, perhaps a little bit of DFT calculations to find information about, for example, density of states of new materials. Then we plug everything into physical models that can be tuned on or off depending on the type of structure we want to simulate. And then everything is coupled consistently with the Fermi-Dirac statistics in order to have a simulation that is as close as possible to what we really measure. Because one important point over here, the simulation is always an iterative process between what you measure and what you simulate, so that you can keep on calibrating your modeling. And the output, of course, are diverse. You can have band diagrams, you can have a spectral response, you can have JV characteristics and the breaking down of losses and so on. So based on this modeling method, I would like to start working on this archetype of FBC architecture, front-back contacted architecture, that is essentially based on a silicon heterojunction technology. You have a wafer, crystalline silicon wafer, that is decorated with the passivating layers on front and rear side, first with the intrinsic amorphous silicon as a standard technology, and then N-type or P-type layers with the TCOs, transparent conductive oxides, and then metallization. So I already mentioned that this structure has achieved the 26.81% certified. So at this moment is one of the world record type of solar cells. And essentially how it works, when we draw a cross-section line across the whole device, this is what we can imagine to be happening. Upon illumination, you can have the formation of course, the photogenerated carriers. And because of the asymmetry in the doping between the transport stack, between electron transport stack and the whole transport stack, we have this asymmetry in population of charge carriers. So on the one end, for the N-type side, direct tunneling and the thermoionic emission are the working mechanisms for which the electrons are collected at the TCO side over here. On the other side, the holes have a little bit more troublesome path to be collected and actually to be recombined with the electrons coming from the TCO side. And essentially here, on the first interface with intrinsic amorphous silicon, we talk again about direct tunneling and thermoionic emission. But then depending a little bit on the material quality and the way how the P-type layer is deposited, depending on its nature, we can have more or less energetically favorable mechanisms that can allow this hopping of holes towards the recombination with electrons on the TCO side. That can be the tunneling assisted trap assisted tunneling, or the bend-to-bend tunneling. And from an energetic point of view, of course, we would like to always come into the situation where the bend-to-bend tunneling is the one that is always active or preliminarily active in this type of transport. So how to tune this optimization? Essentially, we look at the activation energy of the doped layers as well as the carriers concentration in the TCOs as two turning knobs for which we can have the best possible transport of majority carriers at these two sides of the wafer. And of course, the most interesting side is the P-type, because we have also possibilities for electrons to go across this barrier over here. So it is very important to tune especially the P-type layer in order to have the best possible transport in this type of devices. So in these two heat maps, P-type contact and end-up contact, we run essentially a variation of activation energy versus carriers concentration in the TCO. And every colored pixel is the information related to the contact resistivity of that stack when we consider a TCO and we consider the doped material on top of the passivating layer. And you see here that, of course, in both cases, we have a kind of target that looks into relatively low activation energy and a relatively high doping carriers concentration in the TCO. When we hit these two parameters together, of course, we will have direct energy transitions, and of course, the minimizing the contact resistivity means, as a proxy, also improving the fill factor of your device. So in this respect, when we hit both properties, we can also have an efficient carriers collection. Now, what I would like to postulate is that, of course, when we go to low activation energy material, you cannot do it with any type of materials. Essentially, you need to go into nanocrystalline type of regime for your plasmas, and also look into relatively wide bandgap materials, because all in this way, the activation energy can be minimized, because the bandgap of this doped layer can essentially include a higher band bending at the interface with crystalline silicon across the intrinsic amorphous silicon. So what we did already a couple of years ago, we changed massively in a very large parameter space the plasma conditions and gas mixtures in order to create a database of materials that could hit these very diverse optoelectrical properties that can be then used profitably in our solar cells. So for example, we went on looking into nanocrystalline silicon oxide, and in this case we could go for a relatively low refractive index that could help with the optics as well of the device, but also looking into the activation energy, we could get a number of solar candidate materials that can have activation energies well below 100 millielectromoles, as well as some that can go as low as 50 millielectromoles. And for all these, let's say, good materials, we saw that the crystalline diffraction from Raman spectroscopy was always relatively higher. So this kind of proved the point that when we want to go for low activation energy materials, you need to develop nanocrystalline silicon layers with your plasma processes. Of course, I'm talking about silicon-based layers that all in this way can help in getting higher and higher the efficiency. So after a couple of years, of course, these innovations have been picked up, and this is one of our collaborations with industry. Longi, as well as many other companies in China, have picked up this type of ideas together also with previous innovations from other European groups to make a kind of roadmap. And when we talk about nanocrystalline materials at both front and rear side of silicon heterojunction, we talk about HIT 3.0. That is the kind of ultimate evolution of silicon heterojunction technology. And you see that also at the industrial level, all our postulations came true. Very low activation energy, very high crystalline diffraction, and essentially a bend-to-bend tunneling happening in order to have the best possible efficiency. Here, we are talking about a fill factor that is in the range of 87%, which is unheard when it comes to crystalline silicon solar cells until a couple of years ago. We thought that only gallium arsenide could get that type of fill factor. So starting from this point, of course, I would like to step one moment back and look at what we have been doing in Delft in order to make good use of that information that we could get from these optoelectrical simulations. Essentially, as I said before, into an iterative process, we kept on refining our models and also refining better our experiments in order to go over the years from around 18% up to 24% in a number of runs. So the first thing you do with crystalline silicon, you double-side texture it in order to have good light management with your wafer. And the first important thing is to surface passivate it. The atomistic termination of crystalline silicon is full of dangling bonds that need to be passivated. And of course, amorphous silicon, but also hydrogen play a crucial role in this job. And here, next to the intrinsic amorphous silicon hydrogenated, I also mentioned the so-called HPT, hydrogen plasma treatment, that is essentially a way how to tune the properties of the amorphous silicon as it grows on top of 111 crystallographic orientation that comes out the etching of your 100 oriented crystalline silicon wafer. Essentially, if you don't use this hydrogen plasma treatment, there are high chances that your amorphous silicon will grow epitaxially on your pyramids, giving then a very poor passivation property. So here we had to tune a number of parameters, and then we also learned how to kind of back etch and then re-deposit amorphous silicon in a way that our key performance indicator, that is the lifetime carriers, lifetime of minority charge carriers, could be maximized. So by only using these two very thin layers of about 4 to 6 nanometers, we could get routinely 10 to 11 milliseconds. Then, as I said, the next point is to decorate this passivation layer that has to be thin enough to let the charge carriers to go across, is to decorate it with the doped layers. So I already mentioned that amorphous silicon-based doped layers are not really interesting. They are absorptive. They are also not that conductive because the doping activation in those type of amorphous layers is not that good. So we following from the modeling side, we started to develop nanocrystalline silicon or nanocrystalline silicon oxide that ultimately, despite being an addition to the initial passivation that was only of chemical nature, now because of the doping concentration as well, especially in case of N-type, we could keep also in check the passivation with also the added electrical field component of passivation. With the N-type based symmetric samples delivering more than the double of the initial lifetime. Then we pass on transparent conductive oxides that are a crucial type of materials that are also extremely needed for this type of architecture. I'm sure that Monica later will deep dive much more into TCOs, of course. In our case, we developed a number of indium-based TCOs, like fluorinated or tungsten-doped indium oxide, with much better performance with respect to the standard ITO in terms of transparency and also conductivity. Of course, we are very well aware that indium is a critical raw material, is not sustainable on the long run, so we are of course also looking into indium-free or indium-less approaches in the near future. Then finally, in order to get charge carriers out of our solar cell when it is connected to an external circuit under illumination, we need to also make some metallization. So in this case, I would like to present our metallization scheme. Typically, for the front side, we use copper plating as our standard baseline nowadays, where essentially we can make very narrow lines, very high aspect ratio that can give very large opening area for light to be incoupled, as well as a very good conductivity in the bulk of this copper line. So putting everything together, we could get one of our best silicon heterojunction solar cells in the range of 24% with an area of 4 centimeters square. And this type of architecture was essentially the basis together with the TNO and the University of Eindhoven, the basis for what Albert mentioned before, to have one of the earliest demonstration of 4-terminal devices where perovskite and the crystalline silicon heterojunction were combined together. one way how to look at how we progressed is to look at how the fill factor evolved, because the fill factor depends on VOC largely, and also, of course, on the conductivity of the materials involved, but it also depends on the way, how much you can actually collect in terms of photogenerated carriers. So it's a kind of a bit of everything. So when you have the fill factor in check, that is as high as possible, as high as the architecture allows you to do, most likely you also have a very high efficiency with your devices. So that's why we choose the fill factor evolution. We started with a very much scattered material that could give erratic efficiency numbers, and also it was relatively difficult to reproduce. Then with rigorous device simulations, we started to put in check all our doped layers with the nanocrystalline silicon-based doped stack. Then we also developed further the bilayer for amorphous silicon deposition for the passivation, then different TCOs, and then copper plating up to 83.3%. So this is something that it's a kind of, for us, a learning curve, and what also typically has to be done with the all new PV architectures in order to get to extremely high efficiency. Now, if you ask me what's next, for our university, we don't have 24/7 operations. Reproducibility is a very difficult thing to obtain. So in this respect, 83.3% is a very high fill factor for a university solar cell. Then we went on to deposit also different type of solar cells, from a monofacial to bifacial stack, in order to see how much we can push down the thickness of the TCO with respect to the utilization of copper plating. And you see that we can have relatively good devices in both nanocrystalline silicon-based doped layers, but also when using transition metal oxides as a specific case for whole transport layers. And especially in case of moly oxide, we have for both mono and bifacial representations world record certified efficiencies. And in this respect, I would like also to mention that despite losing some efficiency, of course, in case of bifacial, because here we are measuring the devices without any back reflector. So in case of bifaciality, in open field, this number would be, of course, higher. But then the standard is that we need to measure with non-reflective chuck. But what I want to put the accent on is that despite having lost some efficiency in STC conditions, we can use much lower TCO, for example. And in this respect, minimize already, in some ways, the use of indium in this technology. Now, upscaling steps, we went on 4, 9, 36 centimeters square, and now we are, of course, stepping up our work with the uniform PCVD layers up to M2 plus sides, uniform TCO layers, and we have also started with copper plating and copper-based metallization on large area devices. These are all M2 plus wafers. So we don't have yet complete large area devices, but all the key blocks are there. So now we only need people to work on these topics. And of course, the solar NL will be one important outlet for that research. And this is part of the Delft PV Technology Center, where we have, among other things, also a fully developed perovskite deposition line, where we focus very much similarly to a previous talk on wet chemistry, as well as on evaporation, either co-evaporation or sequential evaporation of our devices. In this case, we can also go to up to M4 size wafers, so slightly bigger than M2 plus for future development. Now, this brings me to the third part of my talk, to numerically optimize what is left to be optimized, yeah, in terms of crystalline silicon technology. So I go back to this initial device, already state of the art, very difficult to beat. What is still missing here? For this type of device, 130 micron thick, we are still lagging behind 2.5 milliamps per centimeter square with respect to the green limit that would also be nice to exploit. And of course, it would be fantastic to have better lighting coupling. That means a higher current, higher VOC, higher fill factor. But aside going into very aggressive nanotexturing that would prove to be challenging to keep good passivation, what we would like to propose, it's a new type of solar cell architecture. We call it localized contacts, where essentially we keep the N-type layers only under the metallization, keeping the rest of the device completely open for receiving light. Essentially pretty much like a kind of local IBC device. Now, this is, of course, something that we want to optimize, but we have also started to work on from an experimental point of view. The results will be presented this autumn in Japan at the Asian PVSec, but I can already mention that we are extremely happy that with the nowadays crystalline silicon quality of the wafers, we can essentially keep VOC and fill factor unaltered after all process, and actually boost by at least 9% the short circuit current density with respect to the reference with the full area deposited the layers. So this for us has a huge potential also from industrial perspective. So can we go over 27% with FBC? Here I define the pitch, the distance between two consecutive fingers, and the width of the finger is 10 micron. This is completely industrially feasible. It is possible with the both screen printing and the laser-fired patterning. So nothing really out of reality here. And what we do, we run different crystalline silicon thicknesses versus different pitches. And of course, as expected, the larger the pitch, the more light you let into the wafer. So the top right corner is where the JST of the device would be optimized. Then you have the VOC, which is largely independent in this case from the pitch. It only depends on the thickness of the wafer. And then the fill factor gives essentially the opposite behavior over here, where for thinner wafers and the smaller pitch, you can get better, of course, collection. So in this case, by combining everything together, we can already predict a 27.8% efficiency with a reasonable pitch, again, fully producible at industrial level without lithography, where JST and fill factor play the trade-off point, and you only need to choose which thickness you want to work on. Then what further can be done is to have resistivity wafers that are as intrinsic as possible. And this is something that a couple of years ago was not even thinkable, because you need doping to keep in check the deep level defects in crystalline silicon bulk. But nowadays, the way how we can pull out ingots from a molten material is so high quality that you can afford to have almost intrinsic wafers. When you do that, you can also further improve your efficiency up to an ideal 28%. Then in the last part of this chapter, I also would like to show the ultimate type of architecture where essentially you don't need to put any metal in front, you can just keep both polarities at the rear side, and this is what we call interdigitated back-contacted device. We optimized the full textured case, where HTL percentage is the ratio between the width of the emitter or the HTL over the area of the length of the full pitch. Why I do that? Because then together with the intrinsic amorphous silicon and the doped layers thickness of 10 nanometers fixed, we can again make these heat maps where we combine crystalline silicon thickness versus pitch. And in this case, because it is an IBC, it only depends on the thickness of the wafer, the way how you want to optimize the JSC. VOC goes in the opposite direction, nothing new here. And only what things change, similarly to the case before, is that also the crystalline silicon thickness for IBC devices has to be decreased if we want to push the efficiency further. So this is what we have found so far, and it can go as thin as possible and as fine as possible, but then of course you hit the barrier of technological implementation. So this is something that we still think is more or less feasible at relatively normal costs, but of course going anything further will only prove to be more or less just an experiment. It's not going to change much. Also in this case we did the effect of wafer resistivity, and if you go for very narrow lines that possibly you can only make at one point feasibly with lithography, still it is possible to push up the efficiency. And if some of you is interested in what about TOPCon, or what about what is called the XBC, which in a jargon from industry is the combination between a heterojunction and TOPCon together, we did the same exercise. So at one point, as I said before, different working mechanisms, which I did not propose today in this presentation about TOPCon. Different working mechanisms with respect to heterojunction still allow us to go and push the efficiency to very high values, and only with a good modeling framework you can see the differences besides or beyond these numbers that look more or less similar. So this brings me to the conclusions of my talk. We looked into excellent passivation and transport that can be attained by high quality state-of-the-art crystalline silicon architectures. For a matter of time, I didn't propose all the things that we have studied. There is a paper coming out. So we looked into many different architectures, and essentially we have ranked them as a function of the ultimate efficiency that you can obtain with them. Now, I don't want to pass the message that we should go immediately for this one. I would like to mention that there are a number of very interesting and possibly cheaper options that are also very much efficient, that could also make a very interesting industrial case for industries that are interested in joining this field. So with this, I would like to thank you for your attention. And Albert mentioned our online education, so you can scan through here our website where you can maybe give a look. And also for this summer, we have the PV System Summer School in Delft, so anybody interested can apply. Thank you very much.
Thank you. Very impressive. Thanks very much. There must be questions. Who wants to start? Yes, Alex.
Yeah, thank you for your talk. It was very enlightening, brilliant.
Thank you.
I do have a question about the TCO at the backside. If you have a regular back metallization in the heterojunction, is it also the indium dope layers that are implemented there, and could you replace those, as in the hybrid IBC case, for example?
Look, there are two very important points here. As long as you have the rear side texture of your wafer, you need to have a kind of semi-dielectric material to dump plasmonic absorption that is given by the exchanging momentum between photons that come from different angles and the texture of your material. Yeah. So if you have, for example, a direct metal semiconductor interaction, you are going to lose a lot of light over there. So you need to have either something intrinsic, or like a silicon oxide or MgF2, as demonstrated a couple of years ago in Arizona State University, or in Neuchâtel at EPFL, or you need to use a TCO. And in this case, the TCO comes as a dual function, because not only dumps this optical loss, but also gives you conductivity. Yeah. Now, coming back to the use of indium, because you need to have a TCO, otherwise the solar cell will not work well, or it will not work at the highest possible level. You need to, again, look into my very first heat map, where you need to look into not just the charge carriers concentration in your TCO, but also about its work function. So as long as you have a TCO that fits with a work function between 4.5 and 5.5 electron volts, and a charge carrier concentration in the range of 10 to 20, in principle, you can make the job. And we are, in fact, looking into indium-free materials, zinc oxide, tin oxide, and similar, that can do also a relatively good job. Of course, you need to have then good lateral conductivity. If you want to go for bifacial devices, you cannot afford to have a not that conductive material. If you go for a fully metallized back contact, you can go for something that is not that conductive, because most of the things will happen vertically. But if you have bifacial, part of the collection will be horizontally, so you need to have good sheet resistance there.
Okay. Who next? Yes, Monica.
Thanks, Olindo. Very nice presentation.
Thank you.
So I really like the dark technology that you showed. That's like very specific, because you have this localized contact. But
Yeah.
do you have passivation in the front?
Yes.
The blue layer passivation?
Yes.
Okay.
Yeah, I didn't dive into many details,
I think it was 28.
but it's essentially very much straightforward. Essentially, we do everything here, then we do some back etching that has to be optimized, and there are a lot of tricks to work on that. This is essentially a silicon nitride that we deposit after the metallization.
Okay.
So it is not sketched here because we are talking about 60, 70 nanometers on top of 5 microns of metallization, so you can pierce through it and do the measurement anyway.
Right.
But this type of, I mean, in general, you can use any dielectric that can give a good passivation with respect to silicon.
Okay.
Could be also silicon oxide, but then it becomes too thick, then optically you have to do other tricks to do anti-reflective effect. So in our case, the best material so far is just a plain hydrogenated silicon nitride. That works very well.
That will passivate.
Yeah.
And just as a follow-up, because now you mentioned that you are etching, so
Yeah.
we are like removing all the TCO. Did you already think about ways to just locally deposit the TCO?
Yes, yes, and
Can we
this is actually will be one of the primary aspects of the one of the PhDs in solar NL.
Oh, okay. So reduce
So
it.
of course, yes.
Okay, who would like to be next? Yes.
Yeah, because maybe just to add a very tiny thing, because of course the deposition of TCO will always happen full area in the reactor, but then of course there are now companies that can recycle the indium that has been put on the shields or on the metal masks across which you do the deposition. So although you use and deplete the full TCO target, still you can recycle it at that point. Exactly. Yeah.
Okay, go ahead.
Yeah, my question was related. Also, sorry, very nice talk, by the way.
Thank you.
So, because you basically TCO is just under the metal contact, do you still really need a TCO because you don't have? I guess you don't have.
That's also a very interesting question. You would be tempted to say yes, but it depends on the quality of your N-type layer, how thick it is, and if you can afford to lose a little bit in fill factor. If we had a front junction case, you cannot avoid it. You cannot escape. TCO is really part of the collection of holes. You cannot avoid that in case of P-type stack. In case of N-type stack, if you remember maybe I can go back a couple of slides. Okay, so it's many slides. If you remember the N-type side, you have a direct tunneling throughout the N layer and the TCO, and after on you get directly to the metal. So the N-type, you can afford to not use it, but then your N-type material must be a little bit more conductive and also relatively thin in order to not lose too much in this transfer process. So it depends.
And related to this, because your back contact is a reflector also, so it's the combination of transparency, electrical conduction, that all together you need to optimize.
Yes, exactly. So in this case, if I understand correctly your question, you are referring to this TCO, right? Yeah. So this one, you always need to have it. Yeah. Either when it's fully metallized, but even when it's open, you could even enter into the further optimization that it depends on which type of spectrum you will receive from the bottom side. Whether pebbles or grass or sand, they will have different spectral reflectances. You can also choose the right TCO that has a little bit of window in that specific spectral reflectivity. In this case, the TCO is already obscured by the metal itself, so its working principle is mostly electronic. In case of N-type, you can avoid it, possibly.
Okay. Maybe I can ask the last short question. You mentioned about the texture. You could do better light trapping if you had a more aggressive texture fabrication process. What did you mean with that?
For example, in the past, we worked on what is typically known as black silicon. You can make black silicon in many different ways. You can make metal-assisted chemical etching, deep reactive ion etching. We went for deep reactive ion etching. And you can get essentially zero reflectivity with fantastic angular resilience. The problem is that you cannot get any charge carrier out of your device if you don't passivate it well. And one way to passivate it is to essentially make sure that you're at the really atomistic level, you remove all those silicon atoms that have been displaced by the reactive ion etching. So we typically can do some kind of TMH based defect removal etching that allows us to get back good passivation, but then you lose the anti-reflectivity because everything from TP becomes a little bit more rounder. And then, it's always a trade-off, unfortunately. So that's why we don't want to give up any good optics as we do here, because as also she said this morning, it's important to have even a nanopyramids nowadays that can ensure very good optical effect. And we just want to work on what we do best, which is the passivation at this moment.
Understand. Okay, thanks very much. Let's thank Olindo again for a
Thanks.
fantastic talk.